body is vibrating only with the frequency of external periodic force. This is known as forced vibration. So we can say that forced vibration is a vibration in which, or we can say that the vibration in which the body or system oscillates with a frequency of externally applied force is known as forced vibration. Some examples of a forced vibration are the vibration of air columns in cones tubes, vibration of a sounding boards of a sonometer or musical instruments, etc. Now we will consider another. So this is the maintained vibration, then forced vibration, another is your resonance. And before these three we have already discussed two. One is free undamped vibration, free damped vibration, then maintained vibration, forced vibration, last one is your resonance. What is resonance? Resonance is a special case of a forced vibration. All of you remember, resonance is a special case of a forced vibration when the frequency of external periodic force equal to natural frequency of the system. When omega 1 equal to omega 0, then the forced vibration is known as resonance. So resonance is a special case of a forced vibration when the frequency of a driving periodic force equals to the natural frequency of the system. This is called resonant. This is called resonant. It's different names. Resonant forced vibrations. These are given in different books, but in our book we have collected from different books and we have written a text. Resonant.
Can you explain transition state?
Resonant forced vibration or resonant vibrations, or simply we are saying resonance. Or in some books it is written that sympathetic. Yes, anybody asked say something?
Sir, can you again explain transient state, sir? Transient state and resonance difference, sir.
So when we have applied some external periodic force, initially we have considered a system or a body which is vibrating with its natural frequency omega. Clear? Now we have applied some external periodic force having frequency omega 1 upon the system or the body. Initially we observe the body or the system vibrates with both the frequency omega 1. In the motion we have observed both omega 1 and omega 0 are present. That state is known as transient state. As time passes on, this one will decrease. Already we know, pre-damped oscillation. So this force will decrease. So the force or the motion due to this impressed force will dominate over this natural frequency. So as time passes on, we will observe that the body is finally moving with the frequency omega 1. That means at that time, this force diminishes, that natural frequency diminishes. So body will vibrate only with the frequency omega 1. This state is known as steady state, and the vibration of the body is known as forced vibration. So forced vibration, we can say that the vibration in which the body vibrates with its the frequency of external periodic force is known as forced vibration. Or if you give the lengthy definition like that, you may write down like this. When the body vibrates under the influence of our external periodic force of frequency omega 1, and its frequency of vibration is also omega 1. Its frequency of vibration is also omega 1, which is different from its natural frequency. The vibration of the body is called forced vibration. Now clear? Then analytical treatment, like the previous case, mathematical analysis of forced vibration. What we have done in case of a damped oscillation, we have derived the equation of motion, then we have tried to find its solution. Similarly, also here we will do, this is what we are considering. Damping force P dV of PV or PdX by dt. Suppose we are considering this is 0. We can say that is here x, here minus x. This is the rotor. And we have applied some external periodic force F0 sin omega 1. Okay, let us consider a body of mass M, which is capable of executing damped and simple harmonic motion and subjected to an external periodic force of a constant amplitude and frequency. Amplitude means we have said F0 and frequency means omega 1. Suppose x is the displacement of the particle from its mean position at time t. Suppose x is the displacement of the particle from its mean position at time t. Now, what are the different forces acting upon the body? You can see. The first one, restoring force, that is, you can write restoring force minus kx. Second one, damping force, that is minus p dv by pv or p dx by dt. Number 3, here we have said that p is the damping constant and dx by dt is the velocity of the body at time t. And already we have discussed in case of damped oscillation, this relation holds good for small velocity of the body. And the negative sign indicates the force opposes motion. That means which tends to reduce the velocity. And there is the external periodic force, that is F equal to F0 sin omega 1. So these are different forces acting upon the body. This line is okay. So now we can say the net force acting upon the body. Suppose we'll say this is equation number 1. Restoring force, damping force, this is external periodic force. The net force acting on the body, net force acting upon the body would be minus kx minus p dx by dt plus f0 sin omega 1 t. This is the net force acting on the body. Again, from Newton's second law of motion, we know from Newton's second law of motion, the net inertial force acting on the body equal to md square x by dt square, net inertial force, where m is the mass of the body, d square x by dt square is the acceleration. So we can write m d square x by dt square equal to this one. I am writing here. Now we can simplify this one. This is basically okay. So m d square x by dt square plus I'm writing directly p by m dx by dt plus kx, that is equal to f0 sin omega 1t. So k by m, this is also f0 by m. Simply write one step here, then you can write, then you divide by m throughout the equation, you get this answer. Which we can write equation number 5. So this can also be written as d square x by dt square plus gamma dx by dt omega 0 square x f0 sin omega 1t. Where this P by M equal to gamma, K by M equal to omega 0 square, and F0, capital F0 by M equal to small f0. This gamma equal to P by M is the damping force per unit velocity per unit mass. Omega 0 is the natural frequency of the body or the particle. Small f0 is the maximum force of the external periodic force per unit mass. What is the f0? F is if the maximum value of a sin omega t equal to 1, so the maximum f0 is the maximum force. And small f0 is the maximum value of the external periodic force per unit mass. So equation number 6, see, equation number 6, equation number 6 is the differential equation of motion of the first harmonic oscillator. It is an inhomogeneous second order linear differential equation. You may point out. It is an inhomogeneous second order linear differential equation. I think in mathematics you have read the different types of equations in your 10 plus 2 classes, differential equations. So if you have read this inhomogeneous second order linear differential equation, then I think all of you know the general solution of such a differential equation consisting of two parts. One is the particular solution, which is known as particular integral pi. The solution of this equation contains two parts. One is particular integral, known as the particular solution called particular integral. Which is pi, which does not have any arbitrary constants. And second part is complementary function. Which is the general solution of a homogeneous equation obtained by setting the driving force to 0. Obtained by setting the driving force to 0. So the complementary function contains two arbitrary constants which are determined by initial conditions. So we can write the complete solution CS is the superposition of a pi and CA, particular integral and complementary function. Now we will determine one by one and finally we will get the general solution. First we will try to find the complementary function. Complementary function that can be obtained during the transition state. Transient state. Complementary function will be obtained from the transient state. So in order to get the complementary function, we have to equate the LHS of equation over 6 set to 0. That means we will write that d square x by dt square plus gamma dx by dt plus omega 0 square x equal to 0. Now you will see that this equation is same as that of, if you have remember the equation of motion for a pre-damped oscillator, which is the differential equation of a pre-damped oscillation. So in this case already we have studied when gamma is less than 2 omega 0, we have obtained the condition of a small damping. So now considering that small damping, we can write the complementary function that x here we can write as c e to the power minus a gamma t by 2 into sine omega t minus phi. C is the constant. Where c into e to the power minus a gamma t by 2 is the amplitude of motion. Where we see that c into e to the power minus gamma t by 2 is the amplitude of motion, which decays with time, and phi is the phase angle. And the angular frequency, which already we have discussed in our previous case, omega equal to omega 0 square, and so gamma square by 4 square. This is the, and here c equal to x0 omega 0 by omega 0 square minus gamma square. This is equation 9, then 10, this is 11. Where omega 0 is square root of k by u. And the phase angle, already we have discussed in case of tan inverse omega 0 square, gamma square by 4 square root by gamma by 2. Already we know these things in case of split down the oscillations. Because after setting that we applied force equal to 0, but we have obtained equation number 8 is the same as that of the equation of motion of the three-damped oscillation. So we can obtain the solution like this. Now comes to the particular integral. That is, we can say that steady state case. Since we know that the complete solution is the superposition of a Pi and Cf, so we can write Ei is the similar form of that Cf. So we can write x, that is Pi, we can say as a sine omega 1t minus phi. When we write, since this implies the steady state, we have taken, and the steady state, in the steady state the body vibrates with the frequency of the external periodic force omega 1. Hence we have written sine. In the previous case it was sine omega t minus phi. Now we have written it is sine omega 1t minus phi. Where A is the amplitude of the forced oscillation, A is the amplitude of the forced oscillation, which is a constant, and phi 1 is the phase constant of the forced oscillation. So these two arbitrary constants, one is that A, another is phi 1. These are two arbitrary constants which can be determined using the initial coefficients. Now, if we will consider Pi is written, we have assumed, let us assume x equal to this, which is the Pi, and so we can write this one. How we have assumed that this will be the Pi, because already since we have taken that CS, complete solution is the superposition of a Pi and Cf, and already we know the form of a Cf, that is C e to the power minus a gamma t by 2 into sine omega t minus phi. Hence this part is the similar to that of the Cf. So we can find the final solution as Pi plus Cf. So if x is the particular integral, then it should satisfy the equation of motion that is written in equation number 8. So if x is this, then find dx by dt and d square x by dt square. you should find dx by dt and d square x by dt. Now you substitute the value of x, dx by dt and d square x by dt square in equation number 6. That is the equation of motion for a forced damped oscillator. That minus a omega 1 square sin omega t this equal to f of 0. Only substituting the values of x dx by dt, d square x by dt square, we can write this. So this can be written as f of 0 sin omega 1t minus phi 1 plus phi 2. Cos phi 1 cos f 0 sin phi 1 cos omega 1 t minus. Sometimes if I am omitting few steps, all of you try to complete these intermediate steps in your home after the class. Okay. Now since equation number 14 is valid for all values of t, now we can equate the coefficients of sin omega 1t minus phi 1 and cos omega 1t minus phi 1 from both sides. This case is here. Right here. Here this is in left hand side, this is in right hand side. So then we get now equating the coefficients of sin omega 1t minus phi 1 and cos omega 1t minus phi 1 from both sides, we will obtain minus a omega 1 square omega 0 square a equal to f 0 cos phi 1 and gamma a omega 1 equal to f 0 sin phi 1. Now squaring both equation number 15 and 16 and adding, we will get a square omega 0 square omega 1 square square gamma square a square omega 1 square omega 0 square. This implies a equal to again dividing equation number 16 by 15. 16 by 15. Equation number 16 by 15 will obtain tan phi 1 gamma omega 1. Now the displacement and phase angle phi 1 of the first vibration given by equation number 13 and 18 can be represented. The displacement and phase angle of phi 1. You can write displacement x equal to 13a sin omega 1 t minus phi 1. So this can be written as substituting the value of a, that we can write square root of 4. So this is the particular integral. This is the pi. Now we can write the complete solution. CS, complete solution, equal to pi plus CF. So we can write the general solution. The general solution. So the general solution, that is, we can write this as pi plus this. So already we have obtained CF, C e to the power minus gamma t by 2 sin omega t minus phi plus square root 4. So this is the general solution of equation number 6, which is the general differential equation for host harmonic oscillator. Now we will consider, because we have assumed pi similar to that of a CF, then we have written this is the general solution. Now we will test whether it is satisfying that first oscillator conditions or not. Now, the first term, you will see that represents the free damped oscillations of a frequency omega. The first term, this represents the free damped oscillations of a frequency omega given in equation number 10 and gives the transient state or transient solution. Now the second term represents the first oscillation of a frequency omega 1. The second term represents the first oscillations of omega frequency omega 1 and gives the steady state solution. Initially, both the oscillations will be present. Now we see as time passes on, what will happen? Your gamma, the value of a gamma t will increase. So the value of e to the power minus gamma t by 2 will decrease. So we can say that the free damped oscillation dies out. This will be die out as time passes on, because your gamma t will be very, very greater than 1. When gamma t will be very, very greater than 1, then e to the power minus gamma t by 2, that is the exponential function, decreases. Hence, as time passes on, we have seen that free damped oscillations die out and the body will vibrate with the frequency omega 1, which is equal to the frequency of the external period. Okay, so from this it is clear that this is the general solution for damped oscillation, because already we have studied or we have discussed the characteristic. Initially, the transient state where both omega 1 and omega 2 exist, and we have obtained that free damped oscillation. As time passes on, this part diminishes and the body will vibrate only with the forced oscillation. When the driving angular frequency omega 1 and natural damped angular frequency omega 0 are nearly equal, their superposition will produce beats till transient persist. Such beats are known as transient beats. Such beats are known as transient beats. And it will persist till transient state. Smaller the decay constant, your gamma by 2 or gamma, smaller the decay constant, longer the life of beats. Hence, equation number 19 represents the solution of forced oscillation, whereas equation number 20 is the general solution of forced damped oscillator. The motion of a forced oscillator is harmonic due to presence of a sine function at an angular frequency omega 1 of the external driving force. Okay, then phase of already we have discussed tan phi 1 equal to gamma omega 1 by square root of omega 0 square by omega 1 square. Now if we so all of you remember about your CA1 time and date. Time is already 6, we have said 6:30 p.m. Date is 29th April. All of you remember, multiple choice. And any doubt regarding this examination module, or we can say that mode of examination, you can ask to Dr. M.K. Mandal on Thursday, you will take your class. At that time, you should be clear. Anything.
There are 10 questions or 5 questions.
Huh?
10 questions or 5 questions.
10 questions.
Sir, I got a problem regarding the CA1.
Sir,
every question will be MCQ.
Problems. Multiple choice questions will be there. 5 questions will be problem, numerical problems. So 5 into 2, 10 marks. From the beginning of today's class, I have said, those who are not present again you can. This will be 5 numerical problems you have to solve, and these 5 only that reading will get the answer.
Sir, I got a problem regarding the CA1.
The numericals will also be in the MCQ format now.
Yes, everything will be MCQ form.
Sir.
Okay, sir.
Hello, sir.
Hello.
Sir, I got a problem regarding the CA1. Sir, I have a flight on 6:50 p.m. of the 29th from Agartala to Kolkata. It will be really kind of you if you please.
Then we can take on 28. There will be any problem on 28?
Yes, sir. 28 will be done.
Thank you, sir.
Yes. If you, I have not said this date. I have given 2 dates. Time from, because your classes is going on up to 6 p.m. 6 to 7.
The duration of the exam?
25 minutes. Within 25 minutes, all of you will try to give the answer. 1 or 2 minutes may be late, then I will say that
The link will come in mail.
That more you will discuss with Dr. Perhaps whether he will give in MS Team or by mail, it will discuss with him. On Thursday, he will take the class. During the class, if possible today, he will take the sessional class also. Then we can, whether he has given any link today. So now it is clear. Everybody has agree with this time. 28th April, 6:30 p.m. 28th means day after tomorrow, Thursday, at 6:30 p.m. Anybody has any objection or any problem? Did this time? So it is final.